The second part of today's lesson involves using the mole concept with mathematical calculations concerning atoms. One of the interesting things about the dimensional analysis method of solving problems, which is the way we're going to do the calculations here, is that whenever we have direct proportion, we can set up conversion factors. Conversion factors without y-intercepts are important. So really what a conversion factor is a slope to a plot between the two quantities that are being compared. So here I've got a graph of mass of an element versus moles of an element. Got mass of the element, I'm using oxygen on the y-axis, and I've got moles of oxygen on the x-axis. And as you can see here, when we look at the plot, we've got a point here, 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 and here. And we can also say that if we have 0 moles of oxygen, then we should have no mass of oxygen. So this line should go directly through the origin of the graph. With that said, we can come up here and find our slope. Our slope is 16 grams per mole. So what that tells us is that we have a value, the slope of this graph, 16 grams per 1 mole. First of all, this is the molar mass of oxygen. But secondly, this tells us that in 1 mole of oxygen, we have 16 grams worth of mass of oxygen. So we can look at any molar mass that we can find from the periodic table and say that we have a conversion factor between moles and grams. So as an example, something like nitrogen. Nitrogen has 14 grams per every mole. So that means 1 mole of nitrogen has a mass of 14 grams. Okay? So this allows us to use the conversion factor method, dimensional analysis, to solve problems. Okay, so first question is, what is the mass in grams of 3.5 moles of the element copper? Okay, some information first. Our given information is 3.50 moles. We're going to multiply our given by a conversion factor, as always, and we're going to end up with grams. Okay? We want to cancel moles, and we want to have grams left over after the calculation is complete. Definitions like this, when we have grams and grams related to moles, we're always going to have 1 mole. There will not be an exception to that. The definition is in terms of 1 mole. In addition, I'm going to be taking masses to the decimal place that will give me 3 significant digits in my values. That's just to trim down numbers a little bit. The periodic table masses can be rather precise, and generally we don't need the same level of precision that they're giving us. So we're looking at copper. Copper on the periodic table is element number 29, and it's going to have a mass of 63.5 grams, equivalent to 1 mole. So we can then let these numbers follow in our conversion factor, 63.5 grams to 1 mole. And that gives us 222, and that is the 3 significant digits. Go back to the given for sig figs, 222 grams of copper. And that would be the final answer. Now, one thing I did not do, I did not cancel moles, and I should have. So just 3.5 times 63.5 equals 222. All right, next problem. Chemists produced 11.9 grams of aluminum. How many moles of aluminum is this? So we want a conversion factor that's going to lead us to moles of aluminum. Okay. From the periodic table, we can see that every 1 mole of aluminum is equal to 3 significant digits, 27 grams. Okay? This is the average atomic mass from the periodic table. Okay? So we know that we're going to want to cancel grams. We want to end up with moles. So we would have 1 mole, 27 grams. So 11.9 divided by 27 is out to 0.441 moles of aluminum as the final answer. Notice that this problem was the reverse of the previous problem. Next problem, how many moles of silver are in a sample containing 3.01 times 10 to the 23rd atoms? And we want to know how many moles. Okay. Our conversion factor is going to be the relationship between moles and a number of atoms. Okay. By definition, 1 mole, again, here's mole with 1. All of our definitions or all of our conversion factors are going to be in terms of 1 mole, is equal to 6.022 times 10 to the 23rd power. That many atoms, Avogadro's number of atoms. So we want to cancel atoms, so that's going to be 6.022 times 10 to the 23rd atoms, 1 mole. And to 3 significant digits, that comes out to 0.4998. I take that to 4 significant digits so that I can see that it's actually equivalent to 3, 0.500 moles. Next problem. How many atoms of aluminum are in 2.75 moles of aluminum? 2.75 moles aluminum given, multiplied by a conversion factor to get a number of atoms of aluminum. Okay. Again, we know that 1 mole of anything is equal to 6.022 times 10 to the 23rd objects. In this case, it would be atoms. So we have 1 mole to cancel moles. It's equivalent to 6.022 times 10 to the 23rd atoms. So 2.75 multiplied by Avogadro's number. And that comes to 1.65, actually 1.66 times 10 to the 24th atoms. You should definitely be trying these on your calculator to make sure that you get the scientific notation to come out correctly. Next problem. What is the mass of 1.20 times 10 to the 18th atoms of copper? And we want to know a mass. Masses, unless you're asked otherwise, should be in terms of grams. So this would be grams of copper. Okay. We need to cancel atoms, and we need to end up with grams. Okay. We know that 1 mole of copper from the periodic table is 63.5 grams of copper. We also know that 1 mole of anything, including copper, is equal to 6.022 times 10 to the 23rd objects. This would be atoms of copper. Notice that both of these are equal to 1 mole, therefore they are equal to each other. 63.5 grams copper is equivalent to 6.022 times 10 to the 23rd atoms of copper. Okay, so 63.5 grams, that's from the periodic table, and 6.022 times 10 to the 23rd atoms. And that comes to 1.27 times 10 to the negative 4th grams of copper. Okay, next, we want to know how many atoms of sulfur are in a 4-gram sample. So we've got 4 grams sulfur given to us. We want to multiply by a conversion factor to find out how many atoms of sulfur are present. Okay, we know that we want to cancel grams and we want to end up with atoms. Just like all of our mole units in the conversion factors have been in terms of 1 mole, the same thing is going to be true for atoms. There's always a number that goes there. All of our definitions with atoms will be in terms of Avogadro's number of atoms. So conversion factors will always, if atoms' number of particles is involved, Avogadro's number will be there. And for sulfur, if you take a look at sulfur's mass on the periodic table to 3 sig figs, we're at 32.1 grams. So the calculation, we have 4 multiplied by Avogadro's number, and then we divide that by the molar mass of sulfur, 32.1, and that gives us 7.50 times 10 to the 22nd atoms of sulfur.